Hello, greetings to everyone. My name is Tao Mo, and I am really glad to be here to present our research to you. Today, I present to you modulation of seismic energy budgets by bedrock structure of the shallow intraplate MW6 Peterman Ranges earthquake, Australia. As a matter of fact, Australia is determined to be a stable continental region by Johnston in 1996 because the whole Australian continental land is completely contained in the Indo-Australian plate. However, Australia shows an active seismicity over all SCRs with distribution of many small faults. The figure shows the earthquakes in Australia from 1969 to 2019. In addition to the previously identified 4 regional scale seismic clusters, 2 other possible seismic clusters are apparent in Central and Northeast Australia. The Peterman Ranges earthquake, which we will talk about today, occurred within the Western Musgrave Block, which is shaded in green. There are 12 MW/6 recorded earthquakes in Australia since 1900, and PRE is the largest onshore event in Australia in nearly 20 years. Most earthquakes in Australia tend to be shallow, restricted from surface to the depth of 20 km, and therefore the surface rupture is not unexpected for the large earthquake in Australia as well as Peterman earthquake. Also, the Peterman earthquake is the best recorded MW/6 surface rupture event since 1988 because of the evolution of several technologies such as INSA. The figure on the right-hand side shows the detection of Peterman events from INSA data. Additionally, the development of station horizon denser distribution of stations, as you can see here, these 2 figures describe the station distributions in 1988 and 2016. It is apparently that the station distribution have reached a really obvious improvement. Although not all the stations have the record data, but this does demonstrate the proliferations of stations providing sufficient waveforms for PRE events. Previously, a few research have been conducted on PRE for source features and geological correlation. However, only few of them was from energy perspective, and which is really important as it suggests the details of rupture precesses. Therefore, the energy budgets of large Australian earthquakes still remain mystery, and thus the Peterman earthquake provide a unique opportunity to address the knowledge gap for the intraplate earthquake physics and also indicative for intercontinental seismic hazard analysis. In this study, we estimate the radiated energy from moment wave spectrum. Thus, it will be estimated first. The moment wave spectral density function with equation put forward by Houston and Kanamori in 1986 is shown here. The data required to be corrected due to the path and side effect, and as you can see in the equation, the correction methods are geometric spreading, free surface correction, radiation pattern correction, and frequency-dependent attenuation correction, respectively. And all other parameters are shown on the slides. After that, we estimate the radiated energy follows the theoretical framework of Venkatraman et al. In 2006. In the equations, the parameters rho, alpha, and beta are the density, P wave velocity, and shear wave velocity, respectively. And the M function here refers to the MRSDF, which we estimated previously. And what's more, we also estimated the radiation efficiency, apparent stress, and fracture energy with the equations shown on the slides. In this study, we presented a source spectral modeling using P-wave displacement waveform from 324 selected teleseismic records within 30 to 90 degree epicentral distance at range. First of all, we sample the data to 0.05 second and remove the instrumental response. For data quality control purposes, we perform a program signal to noise ratio filter, and only the data with an SNR over 5 will be selected for later processing. And the figure shows 2 examples for the picking P wave and noise window and their MISDF as well. In addition, the data with gaps were removed and winding up with 110 azimuthally distributed high-quality waveforms for the later estimations. The figure shows the location of these stations. From each station, we will have one individual MISDF curve as the result, and it is used to generate the radiated energy for PRE. And the individual MISDF is shown in the gray line, while the red line is referred to the observed average MISF. The result suggests an average radiated energy of 1.52 times 10 to the power of 13 joule with a radiation efficiency of 31%. As you can see in the figure, the black dots are the estimated radiated energy from of each stations, while the dashed line is the average. We also perform a dielectric function to fit the rupture velocity and obtain a relatively high value. And the estimation of fracture energy and appearance jet are also shown here. To eliminate the discrepancies and accidental errors of different stations and quantify the uncertainties, bootstrapping method was applied to estimate a 95% confidence interval of radiated energy and radiation efficiency. We randomly remove and replace 30% of the data in 1,000 iterations, and therefore the confidence interval for radiated energy and radiation efficiency can be calculated. To clarify the radiated energy level of Peterman events, we compare our result with the energies of 159 intraplate earthquakes from IRIS website, whose magnitude are ranging from 5.8 to 7, with depth less than 20 kilometers. Here, we determine the intraplate earthquake following the criteria of resection Echtel in 1995, which is an earthquake with a distance more than 2 degrees away from the nearest plate boundary. All the results are shown in these two figures, from which we can clearly recognize that the radiated energy for Peterman earthquake is just slightly higher than the average value for a wide range of intraplate event with only magnitude of 6. However, the radiation efficiency of PRE is at a high level, relatively high level among that of the 159 events, which is almost 2 times of the average value. The high value of radiation efficiency suggests that the dissipative energy of PRE during rupture processes will be relatively lower compared to other typical intraplate earthquakes. High radiation efficiency usually occurs in an interplate event with a mature fault, which is easy to rupture. And yet, Echtel in 2016 provided an average radiation efficiency for interplate earthquake of 43%. And from here, we can see that the radiation efficiency of PRE is in the middle of the intraplate earthquake and plate boundary earthquakes. And this is consistent with the analysis from previous research that PRE rupture along a relatively low friction strength fault than that of typical intraplate faults, generating a low stress drop as well as a normal to high radiation efficiency. Under that circumstances, the rupture required less fracture energy and then it radiated more. In conclusion, we proved that the rupture of PRE occur along a weak and low frictional fault plane from energy partitioning perspective, which is consistent with a previous theory that PRE rupture mechanically recur phyllosilica foliations and with indications to the seismic hazard prediction for the area with similar geological setting. In this manner, our research emphasizes the importance of combining geological information into seismic energy budget interpretations, which can be an improvement for future seismic hazard prediction for Australia. And that's all. Thank you so much for listening.